Great. Well, welcome to Good News for Armagh. This is a podcast that looks and tries to answer the questions of the universe and of our hearts. And we're delighted to have Dr. Luke Barnes. Luke Barnes is a lecturer in physics at the Western Sydney University. He studied at Cambridge University, where he got his Ph.D. there in astronomy. And the focus of his research has been in the field of galaxy formation and the fine-tuning of the universe for life. So we're delighted to have him along. And I will advertise this. This is the book. I know he's written a recent book, which I haven't actually read yet. That's my confession. But this book is brilliant. A Fortunate Universe, and he's written it in. He's co-authored it with Geraint Lewis, who actually, interestingly, is an atheist and agnostic, and Luke is a convinced Christian, and so it's brilliant to read that. And if I could recommend, the last chapter is brilliant, where they discuss the ramifications or the implications of what it means to be or why the universe is fine-tuned. So, Luke, thank you so much for coming on. We really do appreciate it. Tell us a wee bit about yourself, if that's okay, please.
Yeah, so obviously I'm Australian. I grew up in Australia and did my undergraduate degree at the University of Sydney. Had the chance to live in England for 3 years and do my PhD at Cambridge, as you said. And then had a postdoctoral position of researcher in Switzerland for 2 years. So that was great. And then I was back at the University of Sydney for 6 years as a postdoc, and now at the University of Western Sydney since 2017 or 18, I think. So that's roughly the career. And yeah, I'm an astronomer. I'm a theoretical astrophysicist. So my thing is not so much using the telescopes as taking the data, doing something with it, and in particular doing simulations, calculations, stuff on the computer, all that sort of stuff. In terms of specifically, as you said, how galaxies form, but more widely, just sort of anything we can, as a physicist, we can try and understand out there in the universe, including sort of the place of life in the universe, which is what the book is about. So it's a little bit about my career, at least. Very
good. What about you? What do you like doing? I think you're into cricket, are you?
I'm very much into cricket. Unfortunately, it's been raining the last couple of weeks in Australia, unusually. But yeah, very much into cricket. So yeah, being in Cambridge was fantastic. There was cricket all over the place because it gets dark a lot later, and so played an awful lot of cricket. Other than that,
bat or bowl or what?
Well, I should be more of a batsman, but I do try as much as possible to get a bowl. The way you do that in cricket is you got to just suggest it to your captain. The captain decides who's going to bowl, and so you just sort of gently suggest maybe it might be the time. Just sort of try and warm up a bit in the right way, just on your way past the captain. So yeah, that's my main skill. I was probably better at that than at bowling itself. So yeah,
very good. I love cricket. It's one of my hobbies. So it's nice to meet a fellow cricketer, because I don't meet many of them, if I'm honest.
Right, yeah.
It's trying to explain a big game of chess to people, and that kind of turns them off, So, but
I say one of the things I like about cricket in particular is, and watching cricket, people say it's boring, but no, what it is it only takes up 20% of your attention. You can read a book. That's right. As long as you know just the right time to look up.
That's right.
To when something's happening, you can you're mostly just reading a book.
That's right. And people say you can do that while fielding as well. So,
so yeah, somewhat.
Yeah, it's perfect for a man of my physique. It's good sport for that.
Yeah, indeed. Yeah, me too.
But that's good. You weren't affected by the recent floods. I was reading crazy floods there in Australia.
Not myself, but actually, yeah, there is. Here we are, start of March, and we've had an amazing amount of rain the last couple of days. So yeah, a couple of areas close to, not me exactly, but close to where I am in the sort of southwest of Sydney. Okay. So yeah, not the nicest situation. It tends to be that way in Australia. When it wants to rain, it'll absolutely bucket down. And you'll get floods, and then it won't rain for a couple of years and you'll have droughts. So one or the other.
You were saying just before we started recording that you have been to Ireland, and you've been to Armagh, and you've been up to the observatory.
Yeah, so a couple of times, actually, twice when I was living in England, got the chance to just head over and just sort of be the tourist and head around. I've got a grandmother who would tell us all the time that we've got Irish ancestors and who they are and what they did. And there's apparently a statue of one of my ancestors in a town. So me and my sister got a chance to go and see that in sort of in the east of Ireland somewhere. I should probably remember where that is. Anyway, and then actually promoting the book back in 2016, it must have been, maybe 2017. But Geraint and I actually got a chance to get over to the UK and just talked at a whole bunch of places all around. And as part of that, Geraint knew Michael Burton, who at the time, and I think still is, the director of the observatory, the planetarium there in Omagh. So we gave a talk there a number of years ago about roughly the topic of the book.
Very good. Very good. That's good. Brilliant. Well, here, thank you for that. Well, just one more thing. How did you actually get interested in astrophysics and cosmology? And actually, what's the difference? What's the difference between astrophysics and cosmology?
Okay, so the way I got interested in was in sort of high school. I was good at maths, and sort of when you're good at something, it can sometimes be enjoyable. And then to discover that in physics, this mathematics can actually describe the real world. And then having started a physics degree at university, discovered that actually the physics of the universe was just some of the most fantastic stuff, that the way we could try and understand the universe using these physical laws. So the difference is, so astrophysics, I would say, is just the trying to understand the way the universe works via the application of the known laws of physics. So you try and work out how the sun works, where is the energy in the sun ultimately coming from. And so then the more you understand nuclear reactions, the better you can understand the way the sun works. So that's all astrophysics. Cosmology specifically, and I would put it as a subset of astrophysics, I suppose, but it's about the universe as a whole. So not about any specific thing in it or even any type of thing in it, like the sun or stars, but as a whole, what's the universe doing? So we know it is expanding. So as we look at things, around us in the universe, they're moving away. Everything's moving away from everything else. We sort of have a rough idea of what the universe is made of overall, sort of 5% matter like us, about 25% some other form of matter that we have very little handle on, called dark matter, and then about 70% of something called dark energy, which we have even less of an idea about what's going on there. So yeah, the way we try and work that out is to see the way that light moves from very distant places in the universe, that sort of thing. So yeah, cosmology is about sort of the universe as a whole rather than any specific thing in it.
Okay, very good. That's helpful, actually. So we're here to chat about the fine tuning of the universe. Do you want to just define that for us, if that's okay, just quickly?
Yeah, very quickly. It was noticed sort of 40, 50 years ago, there are these fundamental properties of the universe, like if you remember your chemistry, there's the atom and the electron goes around the outside of the nucleus. Things like how heavy is an electron? Now, it's obviously extremely light, but there's some number there. As we do physics, we end up with a list of, in our best current theories, a list of about 31 of these numbers. And by definition, they're the sorts of things that the theory itself can't predict. We just have to put them in the equations rather than getting them out of the equations as a prediction. We put them into the equations. And then once we do that, the equations work beautifully. But so these are sort of unexplained by the best physics we have numbers at sort of the bottom level of the universe in terms of basic properties of the stuff the universe is made of. What was noticed about 50 years ago is for some of these numbers, not all, but some of them, and a sort of crucial set of maybe a dozen, very small changes to their value relative to the sort of value they could have results in a universe which is drastically different from ours. It's not just a minor little tweak, atoms get a little bit bigger or something like that. Instead, you end up with a universe which is drastically different in the way that complexity can't form. Down to the point where the sort of basic stuff we see in our universe, where things can stick to other things via chemical bonds and all that sort of stuff. suddenly even that sort of basic level of interaction of one thing with another fails at a fundamental level, or the universe expands so fast that things just, they could stick to each other, but they just don't. They're too far away. Everything's too far away from everything else in this sort of hyper expanding space. Or, these are the sort of disasters we get. This is called the fine-tuning of the universe for life, of the range of values that these numbers could have. We find that obviously ours allows for complexity in life and all that sort of stuff. But the range where you get something interesting is actually remarkably small.
So I've seen a lecture that you do, and like part of what you do, what you said earlier on, you build models to see how a universe would develop, and what you do is you would change a value. So something like gravity, you would change its value and build a computer model to see how that universe would develop and grow. And so what you're saying is that the universe that we live in, like the values are uniquely set to make this kind of a universe.
I wouldn't say uniquely. I would say rare rather than unique. It's like hitting the bullseye of a dartboard.
Okay.
There's more than one place in the bullseye you can hit.
Sure.
You can hit at the top or in the middle, but it's a very small spot.
Okay.
But yeah, other than that little nitpick, sorry, that's basically it.
Do that. That's great.
It's you might think that this is just any old universe and here are its basic properties. I just pick any basic properties and something will happen in the universe, which will be interesting. Something will stick to something and it'll be all great. But actually that, when we actually do the calculation, we look into the physics, we do the hard work of actually trying to answer that question. Actually, no. Some of these changes actually result in a remarkably simple universe where, like the periodic table is gone, for example. You can make something that's sort of like a proton and like a neutron, but they won't stick to each other. And so that's the end of that story. You don't have any of the chemicals. You don't have the periodic table. You have like one chemical reaction and one molecule, and that's chemistry done in these other universes.
So would a good analogy being, because I've heard this before, that if you walk into a room, there's a universe generator and it's got 31 dials on it, and they all are set to a specific amount. And if they were out by any, then the universe that we have wouldn't be formed. Would that be a fair enough analogy?
It's not just that it's not our universe that comes out. It could be the case that you fling all the dials around at random, however you like, and something interesting comes out. That could have been what happens. It's just not what happens. There are, I should say, as I said, there's 31, but there's about a set of 12-ish, maybe 10, where there are these sort of fine-tuning, issues or, cases. Most of the other ones, they're sort of they're very weird and obscure. You could probably turn those dials a whole bunch and not much would change in the universe. For example, there's a type of fundamental particle known as the neutrino, and it's produced by the sun, but it interacts so weakly with the matter around us that basically, trillions of them are passing through your body because of the sun right now, and you don't even notice. There are some sort of weird parameters which sort of change some of the weird properties of the neutrino. You can probably mess around with those a little bit and everything will be fine.
Okay.
But if you walk into the room with the universe generator, there's those 10 crucial dials. And if, you hit go and you find a universe which is able to sustain, more than 3 elements in a periodic table, and able to actually make those elements in the universe as it evolves in stars, which form in the universe. If even that sort of basic level of complexity in the universe, then immediately that those dials are in a very small range of the overall, possibilities that the dials could have been in.
Okay. Well, let's dive down into those more fundamental ones, 10 or 12 of them or whatever. So give us a couple of examples, I suppose. What about like gravity? Would that be a good example?
Gravity is a good example. So, for example, if you change the strength of the force of gravity, and for various technical reasons that you can go and look up in the book or in the literature, it's kind of equivalent to making all the particles heavier. So you have to be careful about what you're actually doing when you flip one of these dials, but we can do that and be nice and careful when we do the physics. But basically, if you turn gravity up too much stronger, suddenly anything that is able to sort of hold itself together and run itself off its own nuclear reactions, which we could call a star in whatever universe you've got. Anything that could do that suddenly now has to be a lot more tightly packed because of gravity. And so in those more extreme circumstances, it runs a whole lot faster. Sorry, it burns through its material very quickly. So rather than our universe where a star or of, you know, the sun's size lasts for 10 billion years, you crank up the force of gravity, and suddenly that number starts nosediving, and all the stars, you know, in those universes burn out a whole lot quicker. Mm-hmm. There's also issues there with the overall expansion rate of the universe. Our universe is expanding, as we know, but it's actually quite easy relative to all the possible ways you could make a universe expand, to make one which just expands either way too quickly so that nothing sort of collapses and, you know, gathers together into stars and galaxies and planets and all that sort of stuff to do anything interesting in the universe, or to have it too strong so that actually the expansion turns into contraction and then the universe ends in a big crunch. Okay. So these are the sorts of disasters that start to happen when you mess with gravity.
So I spent my lockdown just reading a lot of the popular cosmology books and trying to understand a wee bit. And I studied geography at university, which means I know how to shade in maps well. So it's a big stretch for me to try and start understanding the universe, to be honest with you. But one of the...
I should say, let me just jump in. I have a memorable car ride, 4 astrophysicists in the car, and we're driving. It was actually, because I was in Zurich, it was somewhere through the Alps down south. And we had a fairly detailed conversation about, none of us really understand how these mountains got here. It's like, we think we understand, the car thinks we understand galaxies to some extent, but like that mountain over there, like I have no idea what the process is. So yeah, you know, I would have to read a whole lot of books to try and understand geography as well.
Yeah. Well, I could shade the mountain in, but
okay, good.
I think I was about it. But one of the things that kept coming up when I was trying to read the material, and there's loads of, like, would it be fair to say, just on a by the by, that the majority of the scientific consensus would be that this universe is fine-tuned? Would that be a fair statement?
Yeah, especially in terms of the published literature in physics journals, there's an awful lot of, you know, skepticism online. But in terms of published papers which actually challenge these calculations, challenge the conclusions at that level, there's really not a lot. Where they're challenged is more on, you might say, philosophical issues, other than anything else. But no, purely on the physics, no. I mean, it's fairly widely accepted that, yes, if you change these numbers, these are the consequences.
Yeah. So I was surprised by that, just how wide it was in the literature. But whenever I was reading, one of the big ones that keeps coming up, or the big constants, is the cosmological constant. And it, like, so would you want to talk a wee bit about that, and how precise is it?
Yeah, so this is probably actually the best example of fine-tuning. So the cosmological constant has a very long and interesting history. Very quickly, Einstein has his ideas about gravity. He derives his equation and publishes his theory in about 1915. And for various reasons, basically, he didn't know that and didn't think it was possible that the universe could be expanding. So he thought he had to make a static universe. So with gravity drawing things in, he thought he had to provide somehow an outward force to balance things up so the universe didn't move, because he didn't think it was expanding. So he introduced this thing called the cosmological constant, which sort of acts like an anti-gravity, so that you can think of it as, don't take this too literally, but you think of it as space itself sort of starts repelling itself. There's an anti-gravity there, not in the matter, but in the space itself. Anyway, not long after that, it's discovered the universe is in fact expanding. The cosmological constant for the moment goes in the bin. We don't need it. It's a possibility, but if we don't need it, then we can just throw it away or set it to zero, whatever. Fast forward, and as a bunch of scientists, astronomers in the 1990s especially, are studying the way that light travels to us from the distant universe, they start to realize and put together the clues that actually, hang on, we need that cosmological constant back. This number is actually, as best as we can measure it in our universe, is not actually zero. So equivalently, you can talk about the cosmological constant either as a property of space or as a type of stuff that fills space and sort of pushes everything apart, and sort of has an anti-gravity to it. Another name for this is dark energy. So it's the dark energy I mentioned before. If you think of it as a form of energy, then it accounts for about 70% of the stuff in our universe.
So 70% of the stuff in our universe is unseen. Is that what you're saying?
Yeah, well, actually, there's also dark matter. So it's about 95% of the stuff in our universe is unseen.
It's comforting.
It's very odd. The problem is, if you detect, when you see something, I mean, literally, right, a light particle of light bounces off it and then goes into your eye.
Yeah.
And if the light just went straight through it, you wouldn't see anything.
Oh, okay.
The problem is with these forms of energy, dark energy and dark matter, is that we only know of their interaction via gravity, and that's the weakest of the forces. So light doesn't bounce off that stuff, which would allow us to see it directly. Anyway, cosmological constant. One of the things you can do to try to work out where this number came from is to say, okay, look, we have a candidate for stuff that fills the whole universe. Actually, when we go to describe the basic stuff that the universe is made of, say electrons, in our theory, they're fundamental. The way we really describe those down at the bottom level is as a field, which is, you could sort of think of it like, there's a great big rubber sheet that fills the whole universe, and what an electron really is a certain wiggle in that sheet which is sort of traveling along. It's actually a wave in this field. Now, it's a three-dimensional field. There's various other stuff going on. There's some quantum mechanics involved. It all gets rather complicated. The point is, there is something in physics which has this, it's everywhere kind of property to it. And it was discovered that actually, if there was a form of energy in the field, in however the field is configured, whatever, arrangement of the field is, if there's a form of energy which is still there when the field when there's no particle there, okay, so whatever this field is, you can still say, I've got a particle detector. And an old school TV, not the new LED ones, but a CRT TV is just an electron detector. An electron whacks into it and a bit of the screen lights up, and that's how you make old school TVs work. Okay, look, you can still, whatever the field is doing, we can still say, I put a detector here and a ripple hit it, so there must have been a particle there. Okay. There's a state of the field where there's no particle in this box, right? So I put a detector there or all around it, and none of the detectors go off. If there's still energy there, even though there's no particle there, that form of energy will act like dark energy.
Okay.
So we seem to have the ingredients we need to make this thing that's causing the anti-gravity, the universe, to expand. Okay. The problem is, when we try and do that calculation of how much energy is there, thanks to all the fields around us, we get a number which is enormous. It is roughly, there's an enormous number here which comes out of the calculation. There's the number that's our universe's value, and then what it would be, or should be, or might be, or could be, or whatever this calculation is trying to actually calculate. The number is 10 to the power of 120 times bigger. So it's one with 120 zeros. So then as a physicist, you go, okay, let's try again. Let's try something else. There's various ways to try and think about this. In terms of fine tuning, though, you've got a sort of range of values that a property could have. And ours is very small in that. Hang on, let me try and, there's the range. And ours is very small compared to that range, the value. But that's not the question. The question of fine tuning is, where can life live over this whole range? Maybe life doesn't care if the universe is, expanding. So the question is not, where did my dart hit the dartboard? The question is, how big is the bullseye? Okay. Here's the range. Relative to that range, you can actually have values of the cosmological constant bigger than our universe and still have some life in the universe. That's entirely possible. But relative to the overall range, even if you start to change some other constants to try and make up for the difference, it's no more than 1 part in 10 to the power of 90. So, 1 with 90 zeros after it. 1 part in 10 to the 90 of that entire range. And so this is the cosmological constant problem. If you're not in that 1 part in 10 to the 90 part of the overall, you completely blow the universe apart if this value of the dark energy is positive. In other words, you don't make any structure or anything interesting in the universe because literally every particle is 1 trillion light years away from every other particle. So, even if the stuff of the universe could make something as interesting as, a person, a human being, if you put them all together, the problem is I'm made of about, 10 to the power of 20 something particles, 23, 25, who knows? And they're all in a rather small, relative to space, place here. But in those universes, no 2 particles ever get close enough to even touch each other. Okay. And so the reason we conclude there's no life in that universe is because we literally don't have any 2 particles touching. If you don't have that, it's a really simple, boring universe.
Okay, that's helpful. And so you've got gravity, you've got cosmological constant, and you said that there were 31 variants of this, but 10 kind of more fundamental ones, 10 or 12. So what are the other kind of, Stephen, what are the other fundamental ones?
Sorry, just to use the terminology, right? There's 10 fundamental ones. Sorry.
I think that's
31. There's 31 fundamental ones. And by that, we mean we can't calculate it. We just have to measure it.
Okay.
There's 10 which are of the kind where unless you get the dial in just the right place, you don't have a life-permitting universe. There's 10 fine-tuned ones out of the 31, 10-ish, out of the 31 fundamental ones. Okay. So I'd say the cosmological constant is probably the best example. There's 3, really 4, I guess. There's another one that sets the overall scale, sort of roughly order of magnitude scale of all the masses of our fundamental particles, like the mass of an electron, the stuff that protons and neutrons are made out of. There's one of those. There's 3 that then more specifically give the mass of the stuff we're made out of. It's up and down quarks, but you don't need to know the details.
They are like a step down from protons and stuff. Is that right?
Yeah, they're inside protons and neutrons. Yeah, protons and neutrons aren't fundamental.
Yeah.
And then there's a couple more, like the initial sort of density of matter in the universe. You can't have it too dense or too sparse. How lumpy the initial matter is, because you don't want to start the universe off just either completely smooth, because then nothing ever clumps together to make anything interesting, or too lumpy, because then you just make black holes. And then you do actually have to worry about the masses of neutrinos and the strengths of the fundamental forces. There's probably 2 or 3 there as well. And I think that gets me roughly up to 11.
Very good. And all of them are very fine-tuned to bring about complex life.
To various degrees. the sort of 1 part in 10 to the 90, that's the cosmological constant. That's why it's the best example. For the sort of overall mass scale of the fundamental particles, I think you're looking at about 10 to the power of probably 30. By the way, I've got a paper, if people want to look this up, called A Fortunate Little Question, a formulation of the fine-tuning argument, if you want to get all the details of how I actually justify these numbers.
Okay.
And then various factors of 10 to the something, maybe 1 in a million for some of these other factors as well.
Very good. Very good. So this is probably where people then start to diverge, because the majority of the scientific community would agree that the universe is fine-tuned on that level. But then you start to kind of think about it and raise your cosmological eyebrow to why it is fine-tuned, and the question of why. Do you think that is that's a justified question, or do you think it's okay to just say like it's a big fluke?
I personally would say no, this is something that cries out for some sort of explanation beyond itself. But I've been surprised actually how many physicists have been prepared to bite the bullet and just say, look, whatever the fundamental properties of the universe are, that's just it. It just is. That's as deep as we're ever going to get with an explanation. So who cares if it would, who cares what would happen if it had been different? You're asking a sort of a hypothetical question anyway. So and I don't subscribe to that at all. In particular, I think if you have a chance to explain something, then you should. Yeah. That for me, in fact, in chapter 7, the second last chapter of A Fortunate Universe, we go through a sort of number of reactions that people have. And that's the first one. Geraint and I wrote that chapter together. And the first one was just maybe it's a coincidence. And the answer we gave, and we're trying to justify a little bit, is just, look, that might be a last resort if we lose all the other options of how we might explain this. But let's at least look through the other options first. We shouldn't throw away an explanation before we've looked for it. We shouldn't say there's no explanation before we've even looked for them.
Yeah. I think the title that you use is Lady Gaga's Born This Way. Is that right?
Yeah, that's one of them. Yes.
I was watching a YouTube clip there of late Christopher Hitchens, and he said about this, not to be impressed with the fact that we are here rather than not here is to be too easily unimpressed. And the point he was making that was you have to push. Like he obviously would find ways to explain this in his kind of way of thinking, but he was saying that you got to take the fine-tuning of the universe seriously. You can't not to be unimpressed with it. It's just not to be unimpressed, Interestingly, Max Tegmark in his book Mathematical Universe went further. He actually said that not to take the subject seriously is, in his words, he said it was to deny the scientific method, because there's something there that needs explanation, and we must go forward and try to find an explanation of it. Would you agree with that kind of statement, or?
I think it would be irrational. I'm not sure if it's against the scientific method though, because fine-tuning is not a standard scientific problem. Okay. So it's not that our theories are failing in any sense, where it's not that there's a prediction and then there's data and then they're not meeting up with each other. That's not the kind of problem that fine-tuning is. It's something that's just a bit uncomfortable, a lot uncomfortable, I would say, about the fundamental laws of physics as we see them. Mm-hmm. And so if you think the natural world is all there is, Tegmark's got a very weird view on this, as he explains in that book. Yeah. But for most people, we'll bracket off Tegmark for the moment. For most, if the universe is all there is, then at some point science will, it's conceivable at least that science goes, all right, that's it. I've discovered the laws and we're all done. I sometimes use the analogy of some chess pieces who discover via watching the way they're all moving around, they actually discover the laws of chess. And then that's it, they're done. I mean, that's their sort of physics is over. So I'm not sure if it's against the scientific method. And I think one of the reasons why, someone who says that actually, no, that once we get to the ultimate law, bottom of the universe, that'll be it, and we're all done, and we just have to be happy with it, is because there's a feeling that if you push further, you push outside of science. If you want some deeper answer to why the universe is this way rather than some other way, well, that's not the sort of thing that science has ever explained. It's a sort of modal question. It's a question of, it's a much deeper question than what, what are the laws of the stuff I see around me.
Mm-hmm. Mm-hmm. And do you think that the reason for the fine tuning, to put it that way, demands an explanation beyond the laws of physics?
So the way I'd explain it is, it's very hard at this point to sort of to justify we should keep looking for an answer over we should just be happy with what we've got.
Yeah.
You start relying on something like the principle of sufficient reason, or however you try and do this. But the intuition, I'd say, is there will be, if we just took, say, the laws of nature as they are now, deepest laws we know of, and we just took those as being ultimate, just as a practice run with, what would we ever do if we finished off physics? Let's just take the laws we have and try to think of them as ultimate and see if we'd be happy with that. Because, if you're happy to stop somewhere, why not stop here? And there's even if there wasn't, some anomalies that we don't quite know how they fit into the laws of nature, there's still this very awkward fact. You might have hoped, and there was an awful lot of an awful lot of quotes from physicists, atheists especially at the start of the century, Bertrand Russell saying that we're just accidental collocations of atoms, and the sort of feeling that this is just this is just any old universe. This is just an accidental universe. There's nothing particularly special. So I love to highlight the fact that we're the third rock from an average star and a typical outskirts of a typical galaxy in just any old universe with just any old laws. Wait a minute, fine tuning. Whoops.
Mm-hmm.
Right. You see how that sort of approach, it better turn out there's nothing special about the universe around us, and then against this backdrop of all these other values, whoops. So there's a bit of a bind there, and I think that the fact that this fine tuning sort of stirs up so many different but very equally passionate responses from different people is precisely because it feels like it needs an explanation, but it feels like any explanation would either take us to a very gray area on the edge of physics, like the multiverse, or out beyond the edge of science altogether.
And it like the argument itself, it doesn't automatically mean fine-tuned God, but what it does is it raises our eyebrow, and then we start to look elsewhere. Would that be a fair comment or way of looking?
Yeah, it affects people differently. If you're just talking about the sort of the psychological effects, I think I got this story. I heard Alistair McGrath say this, but he'd given a talk where he mentioned a few things about fine tuning, and the comment he got from someone in the audience was, "I'm not religious, but something weird is going on here."
Yeah.
And I think that's a nice little summary.
Yeah.
If I was going to try and put it into the form of an argument, one way to do that would just be to say, there's a couple of ways to do that. One way would just be to say, look, if you can see, if you're an atheist or a naturalist or whatever, if you can see why so many atheists were trying as much as possible to highlight the accidental, ordinary, nothing special nature of life and Earth and the sun and the solar system and the planets and all that sort of stuff. If the ordinariness of the sun's orbit in our galaxy was something you were fine with and comfortable with as an atheist, then the fine tuning of life fine-tuning the universe for life should be something that, if you're going to be consistent, should make you extraordinarily uncomfortable, because it's precisely that sort of specialness, not, I wouldn't say uniqueness because that's not entirely true, but specialness, rareness, something picked out about this universe as opposed to the other ways it could have been, that it's the sort of thing you wouldn't expect if we were just any old universe.
And I read Paul Davies' his Goldilocks Universe, and he said,
great book.
Yeah, very, very, very good, very helpful. And he's very honest, especially about the scientific community in ways. And one of the things I kind of noted when I was reading it through was that the scientific community didn't really, not that they didn't accept it, but they weren't drawn to the fine-tuning argument until ideas of a multiverse came along. And I thought that was interesting. Maybe.
Well, the history's a bit weird. He was there, right? So he wrote a very good book, 1983, I think, called, I think it's behind me, The Accidental, no, hang on, I better get this right. I think it's called The Accidental Universe. Yes, The Accidental Universe. So this is even before, there's a very famous book by Barrow and Tipler, which I know is actually in my office and not behind me. But the sort of laying out the sort of cases that I've been discussing, the fine-tuning universe for life. So he was sort of there. It's around about that time that the sort of ideas you would need to get a multiverse, this, maybe there's lots of other universes out there who all bought their ticket to the life lottery and we got the winning one just by chance. The sorts of ideas in cosmology which seem to give life, so to speak, to the multiverse idea, inflation, early universe inflation, those are kicking off in the 80s as well. And Davis, sorry, I should say it's Davis. Paul Davis is right there in the thick of that community as well. He's a very well known and highly respected cosmologist there at the time. For me, so yeah, I'd sort of take his word for it. For me, I actually don't. Yeah, it might be the case that this fine tuning wasn't taken seriously until the multiverse was there. Another way to turn that around was to say that sort of just invented the multiverse to try and solve this fine tuning problem. I actually don't think. I mean, that's a reason to be suspicious of the multiverse hypothesis, but you should be suspicious of every hypothesis in the same sort of way. That's just standard, skepticism. Every idea about how the universe is supposed to work has got to sort of prove itself. It's got to provide evidence and show that it can actually explain some stuff. Yeah. So a sort of initial prima facie skepticism is what I'd have towards the multiverse anyway. But I think that's all that could be justified from the fact that it sort of came out at about the same time that these sorts of books and Barrow and Tipler's book were coming out.
Okay. Sorry, could you hold on 2 seconds there? There's just someone's come to my door. Is that okay? Sorry.
That's all right. Yep. No worries.
Sorry. Can you give me 20 minutes? Is that okay? That's all right. All right. Yeah. Sorry, I'll edit that bit out.
Yeah, no problem.
So you wouldn't subscribe to the multiverse?
For me, again, I'm a physicist. I'm a theoretical physicist. So I know what I want from a scientific theory. You've got to lay it out in equations. You've got to tell me how you think the world is, and you've got to tell me in enough detail and with enough precision that I can take your idea and make predictions about what I should see in the world around me. And in terms of a multiverse theory, the thing that the chance it has to really make some predictions and sort of cement its status as something worth looking at least, is that it should be predicting the values of these fundamental constants. Because the whole point of a multiverse theory is that on a multiverse theory, they aren't just constant. It's the idea that maybe this thing we call the mass of the electron is actually something that changes, and it doesn't change around here very much. But if you go far enough that way, or back in the history of the universe, or in some other bubble, or however you want to set up your multiverse, somewhere out there, or sometime, or whatever, there's electrons out there with a different mass. They're heavier or lighter or whatever. And so if you start to shuffle all of the dials, eventually the right combination turns up somewhere. That in a theory in which those numbers can change from place to place, and the way we're supposed to predict what we'd expect is by looking at what sort of other universes are out there and what sorts of universes can sustain life. Anyway, the point is, you should be able to take a good multiverse theory and make predictions for these constants, especially the 10 that are fine-tuned. It's kind of hard to know what to do with the other ones because there's no sort of selection effect, but never mind. Maybe we could have a go at those anyway. I don't, as far as I can see, the multiverse literature at the moment, and I have a paper published on this, published a few papers on this sort of thing. I just don't see the sorts of scientific models worked out in detail that can really make robust predictions about what we would expect from a multiverse if there was true. Because there's not really when I say the fundamental laws of physics as we know them, we really do know them. They're written down in textbooks. We know exactly what they are. One's called the standard model of cosmology. One's called the standard model of particle physics, right? We know exactly what I'm talking about. Mm-hmm. There's not really the multiverse. There's just a whole bunch of sort of various, half-baked at best ideas hanging around. And the problem is trying to generate predictions out of them is often a very hand-wavy, ad hoc kind of process. Mm-hmm. So I wouldn't say the multiverse is, I'm as a physicist, I'm sort of not bothered one way or the other. Actually, as a Christian, as a theist, I'm not particularly bothered one way or the other either. I mean, I'm not sure this is the only universe. God can do what he likes. But as a scientist, I know what, as a physicist, I know what I want from a multiverse, and at the moment, at least, I'm not seeing that even in principle in these theories, let alone a good one in practice can actually do all these calculations.
That's what you like in reading a lot of the books. That's the flavor that you get. It's an idea there, but people are hesitant about coming forward and saying this is fact, because, well, in one sense, it apparently can't be proven, because how can we actually touch these other universes that we can't see in or out of our grasp, and that, and so, but that's the kind of feeling that I get when you read. Even people that are pro it would have that hesitancy about it. It's interesting.
Yeah, I'd agree.
You're so like you can't say it's a fluke, a multiverse. So you're convinced Christian, so you would say that there would be, and not just from the fine tuning argument, but you would say that there is a fine tuner behind the universe. What brings you to that conclusion?
I should say, as a matter of sort of historical, for me, it's not that I started off as an atheist and then found out about fine tuning and then became a Christian. That's just not how it happened. But the way I'd put it together is, and actually I think this, I wouldn't put the theistic explanation in conflict with the multiverse explanation.
Yeah.
It's not that I'm saying that God is a better explanation of fine tuning than the multiverse, or a better explanation than, say, all future theories of physics. I think the way to think about it is, is there good, solid explanatory work to be done by the idea that there's a reason for the way the universe is like this, rather than all the other ways the universe could have been. Now, I think if we follow that trail from, if you remember, there's just an accidental planet in an accidental solar system, accidental galaxy, in an accidental universe, and then whoops, it doesn't look like an accidental universe. What the multiverse is trying to do is to say, hang on a minute, maybe if there's a whole bunch of physics we don't know about yet, maybe we are an accidental universe in a much bigger set of universes out there. The problem with that is it's, you know, you would then want to ask the same sort of question out at that bigger level. You know, is making a life permitting multiverse the kind of thing that's easy to do? What happens when we do, so we've got these fundamental numbers, what happens if I change them, like the mass of the electron? Oh, but hang on, wait, there's a deeper theory in which the electron is just something that's can change over there or change over here or change over there. But what is that theory and what are its parameters? And what happens if I change those dials? Well, we have no idea. We don't have a theory down there. We've just got a couple of ideas about how it might go. And so the reason I'd ignore the multiverse as an approach here is not so much that I think it's false or it's true or it's science or it's not science. It's just because if we're trying to ask the question, is this reality we see around us, fundamentally, does it look accidental or does it look like there's a reason for it fundamentally? Okay. And the problem with the multiverse is it's basically saying, well, what if it was accidental? That's no good. It's imagining a scenario in which it looks accidental, at least at that level, but we can't actually test whether it's really accidental, whether it just looks accidental. Whereas you might look at the laws of nature and go, hey, they look accidental. But then when we can get into the details and say, well, what if I change this number and change that dial, and actually do the hard work of trying to work out whether, you know, this is just like any old universe or whether there's something special and fairly rare going on around here. We can do that with the laws we have. We can't do that for the multiverse. Okay. So it's not that it's trying to beat beat God at the same game. It's really a sort of, let's change the rules of the game to something that nobody understands, and then nobody wins. Okay. So the reason I'd say that there's sort of good explanatory work for God to do in this scenario on a level bigger than physics. So I'm not trying to shortcut any physics. I'm going to still do my job. Sure. I'm not going to go start writing God in my physics papers. It's, you know, as best we can tell, and you know, if future physics comes along and changes this, then so be it. As best we can tell, the question of, okay, when I look at the fundamental structure of reality, is there something for a reason for the universe to do there? Is there good explanatory value in saying there is a reason for this universe, that it permits life, you know, life, moral agents, and all those sorts of things? That really and truly does some good explanatory work for why things are like they are, rather than just saying, you know, it is what it is. So like God to you would be the best explanation. Would that be a good way of putting it? Or yeah, I guess so. It would be a bit like, I've used this illustration a whole lot of times before. You know, you suppose there's been a robbery at a bank and you go and look at the footage of how they got into the safe, and the burglar went up to the safe and typed 12 digits into the keypad on the front of the safe and pressed enter. And if you're thinking, why those 12 digits? Well, if the robber just guessed, then any digits is as good as anything else. And then you say, okay, is there a chance for a better explanation to come on and explain why those exact 12 digits were put in rather than any other set of 12 digits? Well, if the robber hits enter and the safe opens, and it turns out those 12 digits that he put in were actually the one code to the safe, suddenly you've got something that a good explanation can latch on to. All right, all of these different possibilities for the way the universe could have been, with all these dials, all these other numbers. Is there something for an explanation to latch on to? And in this case, it's the fact that, yes, our universe is life permitting. It does interesting stuff like make structure, but it's one of a very small set that does that, which is the equivalent of only one code only one 12-digit code will open the safe.
Oh.
If a very small set of numbers does something, it doesn't immediately mean you've got an explanation there, right? Because, you know, if you rewind the tape and you see someone walk up and put in 12 digits and hit enter, and then the safe doesn't open, then, you know, you got nothing. But if you've got those combination of those two things, a very small set and a potential explanation, which can come in and make use of that small probabilities, you know, likelihoods, whatever, then you've got something which actually, you know, can illuminate the way that our universe is.
Okay, that's helpful. Well, how did you then come to the Christian faith? Like, how did you become a Christian?
So I grew up in a Christian household, and so for me, the process of it wasn't the sort of rebellious teenage years much. You know, I just said I was good at maths and I got into physics, so I didn't get into too much trouble, to be perfectly honest. But there was an awful lot of questions about hearing so many of these voices from atheists who seemed to know an awful lot more about science than I did, about how, you know, when we really look at the science, we realize that we don't need God. And so there was a number of years there of trying to read, and I say a number of years, ever since then, you know, sort of mid-teenage years, especially late teenage years into university, of just trying to read everything I could in this. Of, you know, I walked into a bookshop at one point, I must have been about 16, and there's a book called The Ways of an Atheist by Bernard Katz. And I thought, well, there we go, I'll read that one and we'll see if that's any good. It's still behind me, and I don't know why, because it's a horrendously awful book. So I thought, oh, I got to get a better sort of atheist. So I went with Bertrand Russell's Why I'm Not a Christian. That's behind me as well. And that wasn't much better. It was definitely better, I'll give him that. But, you know, I didn't find it particularly convincing. Again, once you dig in, you see that the atheist gets to the point where they go, it's better to say that's the way it is than to try to explain something with God. And so it's not really that they've explained everything, or even that science does that. That's a philosophical choice. Yeah. And once you realize that's the choice, suddenly actually all that stuff about science was kind of a smokescreen.
That's helpful. And
by then I've got a physics degree, so.
Were there any positive voices on the side of Christianity?
Oh yeah, so I didn't just read the atheists. I read all, you know, sort of everyone. I grew up in a background that was young Earth creationist,
okay.
Which wasn't particularly helpful, I have to say. Okay. So there was, at the same time of realizing that the atheists didn't know everything that they thought they knew, I was realizing actually the young Earth creationists don't particularly know what they thought they knew as well. I wrote an article about this for Premier Magazine, if people want to go look that up. But there were certainly, I found actually that the philosophers who are Christians were doing actually a lot of good work. Names like, so, you know, William Lane Craig and J.P. Moreland, sort of philosophically minded, you might say, physicists like Stephen Barr is especially good. I found the work of Robin Collins eventually, yeah. Richard Swinburne, all these sorts of names, to sort of realize that actually, you know, behind the smokescreen, it's a philosophical battleground, as it were. And, you know, there were plenty of Christians holding their own on that battleground.
And I suppose that's why you can sit very comfortably being a Christian and a physicist.
Yeah, sort of once I realized I didn't have to defend the idea that the universe is 6,000 years old. After that's pretty easy. Yeah. Again, I still know an awful lot of people who are young Earth creationists, so I don't want to. We can get into that conversation if you like, but it not being in that camp, really it's then. You start to realize there's an awful lot of atheists trying to control the conversation for the last century. That actually these arguments that, oh, if you believe in science, then you can't believe in God, are such an unbelievable smokescreen with no good argumentation behind it. Behind the smokescreen, there's just nothing. There's just such sort of almost ludicrously inaccurate pictures of what it means to believe in God. Like because I believe in God, I've suddenly happy with saying God makes thunderstorms rather than actually trying to understand thunderstorms, as if that's any sort of conflict. I believe there is a rational order to nature because I believe there's a rational mind behind it. It's what almost all of the pioneers of science believed up until about 100 years ago, and then suddenly it gets turned around and supposedly science has evidence against a rational mind behind the universe somehow.
And it is dispelling those myths a lot of the time. I think that is helpful in getting past the smokescreen, as you said. And I just find that helped me a lot whenever I did that as well. It's important to do. Well, listen, look, thank you so much. We really appreciate you taking the time. Appreciate you being with us. Would you have any final thoughts you want to share with us, or?
I should do a very crude late advertisement for this book, which is the one you talked about. Not so much on Christianity, apologetics, all that sort of stuff, but Geraint and I keep getting emails, as a lot of cosmologists do, of people who try and tell us how the universe works.
Okay.
And they have all these sorts of wonderful ideas. And all we wanted to do is write a book that just says, look, if you want to overthrow modern science and enthrone your great idea of how the universe works, here's how to do it properly. Here's the actual data you've got to understand. And here's why a lot of other theories tried to do that and failed. So we'll give you a game plan for actually, being a revolutionary and overthrowing the universe. So yeah, Cosmic Revolutionary's Handbook. So I'll just give myself a very shameless plug at the end there and say thanks.
I'll put a link to both of the books in the description below, and you get them. I would recommend them. Recommend Fortune Universe. I haven't read the other one, but I will at some point, I'm sure.
It's shorter. Hopefully, it's good fun.
Good. Well, listen, again, thank you so much. I really do appreciate it, and thank you for listening to the podcast. And if we can help you in any way, do please contact us. There'll be other podcasts on the way dealing with different topics around building blocks for evidence for God in this world, and so do listen out for that. So thank you again, and appreciate your time.